In this video we establish the constant acceleration equations for motion in two dimensions. Suppose then that we've got a particle moving in the xy plane with constant acceleration given by the vector a, which has an x component of a1 and a y component of a2, where a1 and a2 are constant numbers. And that the initial velocity of the particle is given by the vector u, which has an x component of u1 and a y component of u2. If the velocity at time t is v, then we can obtain an expression for v by integrating the expression for the acceleration. So we could say that the velocity is the integral of the acceleration. And remember, to integrate a vector, we simply integrate the x components and then integrate the y components. So the integral of a1 is simply going to be a1 times t plus a constant alpha, and the integral of a2 is simply going to be a2 times t plus a constant beta. Now the values of alpha and beta can be found from the initial conditions, and we know that when t equals 0, the formula for v tells us that v must equal alpha beta, but when t equals 0 we've been told that v is the initial velocity, and the initial velocity is the vector u1, u2. So in other words, we've got alpha must be equal to u1, beta must be equal to u2, so we've got v must be a1 times a1t plus u1 as the x component, and a2t plus u2 as the y component. Now we can rewrite that as being the vector u1, u2 plus the vector a1, a2 times by t. In other words, we've got the velocity v is equal to the initial velocity u plus the acceleration a times by t. We've got the first of the constant acceleration equations. If r is the displacement from the initial position at time t, then we can integrate the velocity expression to find an expression which gives the displacement. So we can say that the displacement r is the integral of v, so that's the integral of the vector a1t plus u1, a2t plus u2, and a1t plus u1 simply integrates to a half a1 times t squared plus u1 times t plus a constant which we're going to call gamma at this stage. And similarly, the integral of a2t plus u2 is a half a2t squared plus u2 times t plus another constant which we've called delta. When t equals 0, the displacement from the initial position is 0, 0, because we're measuring the displacement from the initial position. So we've got 0, 0 is the displacement. The formula is giving me gamma delta as the displacement when t equals 0. So that tells me that gamma must be equal to 0 and that delta must be equal to 0. So I've got the vector r is a half a1t squared plus u1 times t as the x component. The y component is a half a2t squared plus u2 times t. That can be rewritten as the vector u1, u2 times t plus a half of the vector a1, a2 times by t squared. So we've obtained the second of our constant acceleration equations, which is r equals ut plus a half at squared. The vector r is equal to the vector u times by t plus a half of the vector a times by t squared. So we've obtained the first two vector equations for the constant acceleration motion. And they're very, very similar to what we had in Unit M2 for motion in a straight line. If we now take equation 1 rearrange it to make u the subject. We've got vector u equals v minus vector a times by t. So equation 2 can now be rewritten as vector r equals v minus at all times by t plus a half at squared. And if we multiply that, the brackets out, we get r equals vt minus at squared, but then plus a half at squared. In other words, we've got r equals vt minus a half at squared, which is the third of our constant acceleration equations. Finally, if we add equation 2 and equation 3, we'll find that the half at squared terms cancel out, so we get 2r equals ut plus vt. In other words, we've got r is a half of vector u plus vector v times by t. Now those four equations are very, very similar to the four of the 5 constant acceleration equations that we had for motion in a straight line. The fifth equation for motion in a straight line was v squared equals u squared plus 2as. That equation does have a vector equivalent, but it requires knowledge of something that's known as the scalar product or the dot product of two vectors. And that is beyond the level of the M4 specification. So for the moment, we've just got the 4 constant acceleration equations for motion in a plane. So let's now move on and use those equations in a couple of examples. So the first example, we've got a particle moving with constant acceleration in the xy plane, has initial velocity minus 4i, and 2 seconds later it has velocity 2i plus 10j. We've got to find the acceleration of the particle and its displacement from the initial position when t equals 4. So, to begin with then, we know the initial velocity is minus 4 in the x direction and 0 in the y direction. The velocity when t equals 2 is 2 in the x direction and 10 in the y direction, so it's the vector 2, 10. We don't know what the acceleration is. We know the time is 2. We're not interested at the moment in what the displacement is when t equals 2. So we're looking for the equation which doesn't have r in it, and that of course is the equation v equals u plus at. So we've got the vector equation 210 equals minus 4, 0 plus 2 times a. In other words, 610 must equal 2 times a, so the acceleration must be the vector 3, 5. For the second part, we need to find the displacement from the initial position when t equals 4. So we know that u is minus 4, 0. We don't know the final velocity when t equals 4. We've got the acceleration is 3, 5. We've got the time is 4. And we're interested in finding what the displacement is from the initial position. So in this case, we can use the equation r equals ut plus a half at squared. That is, we're choosing the equation which doesn't have the final velocity in it. So we've got r is equal to minus 4, 0 times by 4 plus a half of the vector 3, 5 times by 4 squared. So that's minus 16, 0 plus 24, 40, which is going to give me 840. So the displacement from the initial position when t equals 4 is the vector 840. For our second example, we've got a particle of mass 2 kilograms, has initial velocity 1.2, 3.6 meters per second, and starts at the point 84. The particle is acted upon by two constant forces, which are 5(1) and 3(-3). And the first thing we've got to do is find the acceleration of the particle. Well, we've got the two forces that are acting on the particle, and they're constant forces, so we can say that the resultant force is the sum of the two forces, which is the vector 8 minus 2. And because the two forces are constant, the resultant force is constant. Using Newton's second law, we can say that the resultant force is the mass times the acceleration, So we've got the resultant force, which is 8 minus 2, must equal the mass, which is 2, times by the acceleration. In other words, the acceleration must be 4 as the x component and have a y component of minus 1. The velocity of the particle after 6 seconds of motion we can find using the equation v equals u plus at. So we've got the final velocity is the vector 1.23.6 plus the vector 4 minus 1 times by 6, which gives me 25.2 minus 2.4. The position of the particle after 6 seconds of motion is going to be found by first of all finding the displacement from its initial position. So using the equation r equals ut plus a half at squared, we can say that the displacement during the 6 seconds of motion is the vector 1.23.6 times by 6 plus a half of the vector 4 minus 1 times by 6 squared, which gives me 79.2 3.6. Now the particle started at the point 8,4. It's moved through a movement of 79.2 in the x direction and a movement of 3.6 in the y direction, which means that it's ended up at the point 87.2, 7.6. For part D, we've got to find the time and position of the particle when it passes through the x-axis. So it passes through the x-axis at let's suppose it passes through the x-axis at a point P0 and that it passes through it at time t. So if r is the displacement from the initial position to the point P0, then we've got r must equal p minus 8 minus 4. But we also know that r must equal ut plus a half at squared. So we've got the equation, the vector p minus 8 minus 4 must equal the vector 1.23.6 times by t plus a half of the vector 4 minus 1 times t squared. Looking at the y components of this equation, we've got minus 4 equals 3.6t minus 0.5 t squared. That can be rearranged to 0.5 t squared minus 3.6t minus 4 equals 0. And that, I'm looking for the positive solution of that, so we've got t is 8.178 seconds. And then if I look at the x component of our r equals ut plus a half at squared equation, we get p minus 8 must equal 1.2t plus 2t squared. We know that t is 8.178, so substituting that in will give me a final value for p of 151.6. Particle crosses the x-axis after 8.18 seconds at the point 151.60. Now before finishing this video, please pause the video at this stage. Just have a look at the question here, where we have another application of the constant acceleration equations in 2 dimensions, and have a go at this question and take your answer along to your next lesson. And that finishes our look at the constant acceleration equations for motion in a plane, but we will be using these equations to consider the motion of projectiles, that is, bodies moving under the action of their weight alone.